So this video will take what we learned in our last section where we were doing that sigma notation and using it to write area formulas. And if you'll notice, that very first formula right here, it looks exactly like our other formulas except for this little I right here. It's saying instead of delta x being the same for each interval, that you can make delta x different for each interval. For instance, if you have some curve and you want to make your first rectangle really skinny, but your next rectangle even skinnier, but then this rectangle here, down here, you make it really fat, but these other ones you make, I don't know, in between somewhere. You can make them different sizes. That's basically saying you can make your delta x's different sizes. It's called a Riemann sum when you make them all various sizes. Not sure why you do that at this particular rectangle. It was just for showing you purposes only. But Riemann sums represent area under a curve on an interval. So to find the area, you add up all n of your rectangles. You use the height, your f of x, how high the rectangle is a y value, and how far apart your two x's are, your change in x. So remember, that means add up all the rectangles. Now, your book has some problems if you want to try some of these, but honestly, the idea is if you're making rectangles, they don't all have to be 1/2, 1/2, 1/2 in width. They can all be different sizes. That's big picture what you need to know. It's okay to have that. Definite integrals also represent area under the curve. And we're going to be talking about how they relate. So definite integrals are when you take the number of rectangles to infinity, okay? You take that number of rectangles here to infinity. So you do the limit of this whole thing. And you don't have to have this xi, just basically is saying you don't have to have all of your rectangles being the same width. Some might be skinny, some might be even skinnier, some might be medium width, and some might be really fat. But we write this limit notation with an integral sign, antiderivative sign. And we've seen that before when we did antiderivatives, just basic power rule sort of things. But it looks like this thing, and it is called a sigma, just like this is called a sigma. This sigma just has that limit implied right in there. And just like the definition of derivative had a limit in it, the limit of that slope function, right? F of A minus f of B over A minus B. This has a limit in it, and that implies that that limit is ingrained right in there. And just like we don't want to have to do the limit every time to find derivatives, we don't want to have to do limits every time we have to find integrals or antiderivatives, definite integrals. So we're going to find the shortcuts to do this, both this time and in the next video, not the section, I should say, 5.4, but each piece has a name. This guy right here is called the upper limit, okay? So the upper limit is B, okay? Similarly, the lower limit is called A. It just tells you the interval you start at. You're finding this area, for instance, if I use my little graphic up above. Okay, it's finding that area from A to B under a curve. Integrals don't exactly mean area, and we're going to talk more about that as this video is on. This is the function, okay? It's called the integrand, and the differential here, this whole thing is called the differential. Okay, it's called the differential. And it also tells you the variable of integration. You're using x. If these two variables don't match, you've got to do all kinds of fun algebra to make them match. They have to match. All right, so that big S, it's called a sigma. It is literally still called sigma. One is like a capital letter and one is the lowercase. I don't know exactly. Don't quote me on all that. But the whole thing altogether, this whole schmackaroony, let me get my highlighter out, this whole thing, that is called the integral of f from A to B. Now, it might be better, instead of writing that integral sign, saying the integral, or even the definite integral. I didn't write definite all the way out. So definite integral of f from a to b. Now, so if we take an infinite number of these little rectangles of height f of x and delta x our width, we can simplify that by writing it like this. And now we're going to talk about how we find some shortcuts to do those. Integrals, definite integrals. All right, since integral means area, if we want to find area under the curve, we want to take the integral. Okay, conversely, if we want to find the area, take the integral. Okay, now it isn't precisely that, and there's a little bit you have to be careful with, but let's talk about what these mean geometrically first, and then we'll go from there. So if I were graphing this first antiderivative, definite integral it's called, okay, definite integrals have numbers here and here. Those are called definite integrals when they have numbers in the upper and lower limits. They don't have to be in order, and stuff happens when the high and low number are switched, and we'll get to that. So we're going to use graph geometry and area formulas to help. Later we use other methods, and we're going to work toward it. All right, so this is our f of x, right? So in my problem right here, my function of integration is 4. If I were going to graph 4, it'd be a flat horizontal line, right? Y equals 4. Okay, if I want to find the integral, or the area, between 1 and 3, I'm going to find 1 on my graph, and I'm going to put 3 on my graph. It doesn't have to be perfect. I'm going to make little dotted lines. If I want to find that area between there and there, that's what that antiderivative means to do, that definite integral. It means find this area. All right, so how do I find the area of a rectangle? Well, that right there, its width is 2. That right there, it's up 4, right? It's at 4. So this height right here is 4. So the rectangle is 2 by 4. It's 8. The antiderivative from 1 to 3 of 4, dx, is 8. All right, next. I'm going to switch colors so they kind of don't run together as much. All right, so this is my f of x. I'm going to graph it. I'm going to start at 2. I'm going to go up 1 over 1. And I notice that I have to do that from 0 to 3. So I'm going to just go to 3. So I'm going to go up 1 more, over 1 more. Don't look at my very bad graphing skills on this iPad. And then I'm going to draw the line. Don't really care over here. Okay, so I'm going from 0 to 3. So I want to find the area between the x-axis and the curve. That's really important. You're going to the x-axis. Just like in trig, when you were measuring reference angles, you always go to the x-axis. Same deal here. Unless this guy says dy, and then it's saying go to the y-axis. But let's, baby steps, baby steps. All right, so if I'm going to find that area, you can do a couple things. You can split it up into a rectangle and a triangle. That's okay. I'm going to remind you of the area formula, though, for a trapezoid. Now, this is a trapezoid with this being base 1 and that being base 2, okay? This is the height of the trapezoid, right? You have to kind of turn your head. This is the base. That's the other base. This is the height between the two bases. The perpendicular makes the height. So h is clearly 3, right? It goes from 0 to 3. That's 3. Count it on your graph. 1, 2, 3. All right. So here, this base is 2. Okay, that base is 2. And this base right here, it goes up to, let's see, we went from 2, 3, 4, 5. We're up at 5. That height right there from here up to here was 5. I just got that by counting on my graph as best I could. You could also, we know that it's at 3, so put in 3. If you put in 3 to your function, f of 3, well, it's 5, right? That's just your f value, your height, your y value, same deal. All right, so now in a trapezoid, the area formula is b1 plus b2 times the height divided by 2. Some people say 1/2 b1 plus b2 times height. That's the same, okay? It's the same. So if I take my b1 plus b2, I get 7. Then I'm going to multiply by the height. That's 3. I'm going to divide by 2. That's 21 over 2, or 10.5 if you want. Done. That area under the curve is 21 over 2. Why would you do 3 rectangles, 4 rectangles, 5 rectangles, whatever, and get an estimate when you could get an exact answer easier, just using the geometry you know? Now, you certainly, like I said, you could do triangles and rectangles. Remember, a rectangle is base times height, and a triangle is 1/2 base times height, but you can do that and just, that's called doing compound areas. That's certainly acceptable. Okay, this last one you have to recognize. That guy is a semicircle with a radius equal to the square root of 4, right? Semicircles are r squared minus x squared, square root of the whole thing. So this guy really looks like a semicircle of radius 2. So it looks like that. Now, I am going from -2 to 2. So I am finding this whole area under the curve. Now, you could make a bunch of rectangles, right? I can make a rectangle here and a rectangle here, but I'm going to get an area. First of all, I'll have all kinds of square roots to calculate with, but I'll also have an area that's clearly above or below to get an exact area. Even if you average them, you don't get the exact area. If you did like an above one and an inscribed angle, rectangles rather, one, you would just not get an exact answer. So how do you find the area of a circle? Pi r squared. So guess what we're going to do? Pi r squared divided by 2 because it's half a circle. So we know pi r squared divided by 2. The answer is 4 pi divided by 2. It's 2 pi. Got an exact answer. I don't need to do rectangles if I can get an exact answer using geometry without doing 4 different calculations that are going to be a pain in the booty. Now, the other thing you can do is, what if I had said instead from -2 to 0? Okay, same function up above my semicircle. I'm not going to rewrite it. It's not going to fit on my screen. Well, if I go from -2 to 2, my children are having a hard time eating dinner. I think I might have to go down and help Daddy. They're kind of throwing a fit. I have to use a quarter circle. So pi r squared, that's 2, divided by 4. Hey, it's just pi, or half of what we got before, right? Instead of 2 pi, it's pi. So you can do other areas based on the formulas. For your comic relief, my children were screaming. My one child, who just turned 6, mind you, was screaming because, and I quote, "Daddy wouldn't feed me." Whew, okay. Comic relief, or stress for Miss Kite, whichever. All right, so if I have some kind of constant function, I'm going to use 7, right? F of x equals 7 is a constant function. And I graph that just like our first example on the other page at 7, right? I'm not going to draw all the tick marks, but that's up at 7. And I'm going from -1 to 3. Okay, it's okay that it's negative. It's all right that you started a negative number. It just says we're starting way over here at -1. And we're going to go all the way over to 3, and we're going to find this area underneath the curve f of x between the curve line and the x-axis. Make sure you always color down to the x-axis. That's just a rectangle of, oops, that's in highlighter still. We're going to undo that. Hit my little pen. It's a rectangle of 4 by 7. Clearly, the x and y axis are not scaled the same. So my area is 28. All right. So this answer for this antiderivative is 28. The area under the curve between -1 and 3 is 28 units. If you have this happening for any constant function, it's going to be your constant, right? That's the c, the function value, the height of the function, times however wide this interval is. But remember, our delta x was always b minus a. So that's a formula you can use. I personally just do this. And actually, once we learn some shortcuts for finding antiderivatives, I actually use the power rule to do this. We'll use the power rule that we were using with the antiderivatives. But also we're going to use something called the fundamental theorem of calculus. It sounds important. It is fundamental. It is called fundamental. It's fundamental. So it's really important. All right, so integrals can be negative. That is important, and this is where things get a little tricky. So I'm going to graph this first one. I'm going to pause to graph it because it's going to be tedious and I'm going to be slow. You do it too. All right, so I graphed mine, and just for quick recap, this is our function. So this is the line I have to graph. That's my y-intercept, my b. and my slope is 2 over 1. So I started at -3, I went 2 over 1, 2 over 1, 2 over 1, 2 over 1. Now you can get the coordinates of each of those by substituting in. Like you could put in 1 and you get 2 times 1 minus 3, that's -1, and there you go, and so on and so forth to get each of those coordinates if you need to. But I graphed far enough out in this case because I want to be able to use the same graph. Notice it's the same function. I'm going to use the same graph for both problems so that I have a little more room. Now, when I want to do this one over here, notice that the upper limit is 1.5 and the lower limit is 0. So it means I want to find the area of this function, this f of x function, that line, from 0 to 1.5. That happens to be this area between the curve, and you always go to the x-axis, so it's up, the line is below the x-axis at that on that interval. So to go to the x-axis, you have to shade upwards toward the x-axis. It's this little triangle, excuse me. Whew, call it the right thing, Kite. All right, so to find that area, you do 1/2 the base. Well, the base right here is 1.5, right? It goes to 1.5. If you want to calculate that, if you're not sure, put 1.5 in, and you'll see that that's the x-intercept. You could also set this whole thing equal to 0 and solve. You get 3 divided by 2, 1.5. All right, this height is 3, right? Just by looking at the graph. So if I do that, I get 2.25, because when you multiply that out, you get 2.25. Now that is the area. It, however, is not the integral. Integrals can be negative. If they are below the x-axis, areas below the x-axis give negative integrals. Now, so to find the answer to the integral, you use the area, but it's negative as the answer to the actual integral. So my answer for this integral is negative 2.25. Yes, the area is in fact 2.25, but the antiderivative is negative 2.25 because it's area underneath the x-axis. Now, to do this other one over here, I'm going to go from 0 again, but all the way to 4. So this time, when I update my area, I'm going to go all the way to 4. And I'm going to grab my highlighter so it's a little different. Alrighty, go away. All right, so that it's this area here as well. Both those pieces go in to finding the total definite integral. So notice this part is above the x-axis though. Well, you still find the area to find the answer to the antiderivative, the definite integral. So we're going to do that. It's 2.5 is the base, right? This part is 2.5. I found that by saying, hey, if this is 1.5 here and that's 4, I subtracted them and I get 2.5. You can also count on your graph. Here, you can get this. I counted. It's 5. And I'm sorry, I'm going to erase this. This looks like some crazy gibberish. 2.5. I don't know why my handwriting was so bad. But this guy is 5. I counted. But if you're just not sure or you're drawing graphs like without graph paper or something, substitute into your formula. I know I'm going to 4, so put in 4. 2 times 4 minus 3, well, that's 8 minus 3, it's 5. So this better be up at 5 just because that's what your function is telling you. If I put in 4, I get out 5 to my function. So calculate that, and you get 6.25 for that part, that area. So now I have the bottom area is 2.25, but it's negative. The top part's area is 6.25, but its integral is positive. So to get the total integral, you have to take both of those pieces. But remember, the one part is negative, so the first part is negative, plus the second part is positive. You put those two pieces together just like you find area. Put this part with that part, and you're going to get the total answer. Same deal. It's 4. All right. So area below the axis is negative total area. You add all the pieces. Okay. So the area technically isn't negative, but the integral, the definite integral, is negative. All right. So if f of x is less than 0 on the whole interval, then this is negative, and you add all the pieces to get that, to get a total. All right. Now, other graphs that you might use, and they might have discontinuities. Okay, so like this guy right here, absolute value of x divided by x. Well, x divided by x is 1, as long as x is positive, right? If x is a negative number, and this is positive, whatever that same number is. So put in, say, 2. Negative 2, excuse me. If I put in negative 2, I've got the absolute value on top, but negative 2 on the bottom. I'm getting out negative 1. No matter what negative number I put in, I'm going to end up with negative 1 on the whole thing. Now, I have one error that I just drew. Because of the function, I can't divide by 0, so 0 cannot be part of the domain. I need to make my endpoints here both open circles. 0 is not in the domain of this function because I cannot divide by 0. All right, so now if I'm going to go do an integral from negative 1 to 2, I have to start at negative 1, go from the curve to the x-axis, and then again at 2, go from the curve to the x-axis. I end up color in the area from the curve to the x-axis, shaded in, and you end up with these two rectangles. So remember, always go to the x-axis. It's where you meet the x-axis. You have some negative parts and some positive parts. This area is 1 times 1 because it's 1 high and 1 wide. It's 1 high and 1 wide, just looking at it after graphing it. This one is 1 high and 2 wide. So this area right here is 1 by 2. So it's 2, but this guy is negative parts of the integral. My total integral from negative 1 to 2, okay, I really need to put a function here, I'm being lazy, is negative 1 for this first part, because it's below the axis, you have to use a negative, plus, now this part is above the axis, so it's considered a positive area. My total answer is 1. Another way to think about it is some people like cancel. This part is equivalent to this part, and they cancel, and then they only find that area. It's just another geometric way to think about it. All right, so if I have this guy right here, it's an absolute value shifted 3 to the right. 1, 2, 3. Looks like a V. Okay, that'd be at 3 there. If you want to put in 3, a 0, you'll see that it's up at 3. But you're going to find the area, it says, from 2 to 5. So I'm going to start here at 2, and I'm going to go, that's 3, 4, 5. Now, I didn't draw tick marks here, so I'm starting at 2, I'm going to 5. It ends up being 2 rectangles. They're both above the axis, but there's some kind of strange going on here. It's in pieces, so you have to find the antiderivative in pieces. It's a triangle plus a triangle. They're both positive. I don't have to make any negative because they're both above the x-axis. But I have to find 2 areas. 1/2, now the base of this one is 1. And the height, if you're not sure, you can always put the x value of 2 in. So it's 2 minus 3, absolute value. Well, it's 1. Okay. Now, if I put in 5 to find this value, f of 5, right? I put it into my f function. 5 minus 3, absolute value. Well, that's 2. So this area right here is area equals 1/2, 2 times 2. Okay, so I've got this area right here. That's 1/2, right? 1/2 times 1 times 1. Plus, I got to do this area, the second area over here. Well, that's 1/2 of 2 times 2. That's 2. So my total area, or my total integral, is 2.5. Area and integral are not always the same. If someone asked for area here, you would say 3. The area is 3. 1 here, 1 here, 2 here. The area is 3. The integral, the definite integral, has these negative things involved. So area and integral aren't exactly interchangeable, but you use area to find integrals. Area can help you find integrals. All right, so how do you do something like this? Well, again, here's our handy-dandy, wonderful semicircle of radius 4. Remember, that's 4 squared, so it goes from negative 4 to 4. We're going to do this guy. Also, remember, if this had a negative out in front, that'd be below the axis. All right, so how do I find the area? It says I have to go from negative 4 to 4. So I have to find that area. and use that, I get a positive answer because it's above the axis. And I better erase that negative that I threw in there just to remind you. Actually, you know what? We're going to do that negative after I do this. So if I do that, I have to do, it's positive. I put the positive there just because it's above the axis. And use pi r squared. It's 16 pi. Done. Now, if I change that, I'm going to change it twice. If I go from -4 to 0, and I do negative square root of 16 minus x squared dx. Don't forget your differential. It changes this because the whole graph is now still semicircle, but remember that negative out in front inverts so that it's below the axis. Now I'm going from -4 to 0, that guy. And so I have, my answer is negative because it's below the axis, but it's still pi r squared, but this time instead of being a half circle, it's a quarter circle. So I get -4 pi. It's negative because it represents only area under the curve, and it's a quarter circle, so I divide by 4 with the area. All right, next one. This was the last one for this video. You need to graph this to get a picture, I think. If you're going from -3 to 8, let's see. I've got a parabola that is starting at, it's shifted to the left one and up 6. So left 1, up 6. All right, I'm only going to sketch. I have some kind of, I said parabola, I'm sorry, absolute value. If I said parabola earlier, I apologize. So I'm going from -3, and I have to go all the way out to 8. Let's see. I can see already that I'm going to have a pain trying to find this value. I can't count easily, and I've got two weird things going on. So I've got this piece here, and I've got this piece here. Now you can certainly split it up into more. I find less is more for me, but I've got a trapezoid over here and a trapezoid over here, and I'd like you to think bigger if you can. So I'm going to come up with values for these trapezoids. Now this one's easy. It's 6. I can see that I put it at 6. If you put in -1 into your function here, you can see that. You'll get -1 x, excuse me, not x, -1, put in -1, -1 plus 1, absolute value plus 6, that gives you clearly 6. So you know this height, this f of x value is 6 there. Now if I put in -3 plus 1, absolute value of that, plus 6, you get 2 plus 6, that's 8. So I can figure that out. This is 2 because, well, the distance between -3 and 1 is 2. This guy right here, that's 9 because you go 8 here plus 1 more. That's 9. I know that this is 6. Now this right here is the one that I find most students have the hardest time because it's just way out there. It's way off the graph. But you can just calculate it. X is 8 there. Put it in your function. 8 plus 1, absolute value of that, plus 6. Looks like it's 15 to me. So that's how you can figure that out. Now we use area in order to find the answer for that definite interval. So to find the area, you're going to find this area, that's a trapezoid, with a base here and a height here. So the two bases are 8 and 6. The height is 2. Divide by 2. Those are going to cancel. That's 14. For this little guy right here, that's 14. Plus, for the big trapezoid, one base is 9. The bases are, excuse me, that's the height. Pardon me. The bases are vertical, right? That's the bases are the parallel pieces. So the height is 9. My parentheses look terrible. And my two heights are 15 and 6. Base 1 plus base 2, and I'm going to divide by 2. So you're going to get a decimal. I'm going to calculate that. You calculate it. See if we can get the same answer. So when we compute that, that was 14, remember. And this one, I got 94.5. Maybe you did too. So in total, my total area is 108.5. And remember, if anything went below the curve, we'd have to do something special with that. So in summary, if you can just draw the areas in under a graph, and those are areas of shapes you know how to find the area of, then use the geometry formulas that you know so well. Get comfortable with the trapezoid formula. It will help you in the long run. And I would practice some of these now on the handwritten properties of properties of definite integrals, I think it's called. I have the solutions there. I would not try to do the back yet.